We are going to discover incredible things that we never imagined.
Designed to tunnel deeper into space and farther back in time than any previous observatory, with the audacious goal of seeing the very first galaxies that lit up the young universe, the James Webb Space Telescope, or JWST, is looking at the universe like never before. And now, in a growing series of triumphs, the James Webb Space Telescope has returned an eye-popping image of over 700 galaxies, revealing new secrets about the origins of the universe. But as famous physicist Michio Kaku said, Webb's findings contradict earlier theories. In other words, our understanding of the universe is being challenged.
Well, that's the problem. The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe.
Join us today as we dig deep into James Webb's new discoveries that debunks the Big Bang Theory. Close your eyes and imagine space, and there's a good chance your mind will pull up a picture taken by Hubble. The Hubble Space Telescope became a household name in the 1990s, as the images it captured appeared on TV and in magazines, newspapers, and movies. Over the decades, Hubble created a shared visual lexicon of outer space and seeded multiple generations' imaginations with visions of glowing nebulae, haunting planets and faraway galaxies. More than 30 years after the launch, Hubble is still going strong. But now its successor, James Webb Space Telescope, promises to outdo it. According to NASA, James Webb can be a time machine, and it all has to do with the speed at which light travels through space. Light moves incredibly quickly, but fast isn't the same as instantaneous. It seems like almost the same thing across smaller distances, like the space between a lamp turning on in your living room and your spot across the room on the couch. One flip of the switch, and the light is already there. But over the huge distances between galaxies and space, that travel time starts to matter more. Even something as close on a cosmic scale as the Moon, which is a minuscule 239,000 miles away from Earth, is affected by the phenomenon. Light that hits the Moon takes about 1.3 seconds to travel across those 239,000 miles and reach your eyes, according to NASA. That means when you look up at the Moon, you're actually seeing the Moon as it was 1.3 seconds ago. That's where the term light year comes from. It's actually a measure of distance, consisting of the space light can travel in one Earth year, at a speed of 186,282 miles per second. Amazingly, the James Webb Space Telescope, as renowned physicist Michio Kaku said, is powerful enough to capture light from galaxies that are billions of light years away. At that distance, the galaxy's light tells what the universe was like billions of years ago. Since the age of the universe is about 13.8 billion years, these distant observations allow astronomers to measure changes over the lifetime of the universe. The awe-inspiring images Webb captured demonstrate that power. When the first photos from the JWST went out into the world on July the 12th, 2022, they were stunners. The clarity and level of detail were unprecedented. Seeing the telescope's new views of some familiar objects, from the oft-photographed Carina Nebula to the planet Neptune, feels like putting on new glasses with a stronger prescription. As Webb's images have been released, each of Webb's images that have been released so far have created a stir, suggesting that in the coming years, the telescope's pictures will infiltrate the public subconsciousness just as thoroughly as Hubble's did. And now scientists are ecstatic with some of the cosmic portraits JWST has given us so far, one of which is the result of the James Webb Space Telescope's Advanced Deep Extragalactic Survey, or JADES, basically the next-gen version of the Hubble Deep Field. But this newest deep sky stare is on a whole different level. With 32 days worth of telescope time, infrared wavelengths that allow JWST to see more distant galaxies than any telescope before it, and a much bigger viewing area than Hubble was capable of. Even as the JADES program continues to collect data, team member Kevin Hainline of the Stewart Observatory and Ryan Ensley of the University of Texas at Austin announced at a press conference of the 242nd meeting of the American Astronomical Society the discovery of hundreds of early galaxies. These galaxies reveal the chaotic state of the universe as it was just hundreds of millions of years after the Big Bang. Specifically, the James Webb has discovered 717 galaxies at redshifts greater than 8, when the universe was just 600 million years old. The most distant of these, the farthest galaxy humans have ever seen, Hainline says, is spectroscopically confirmed to be at a redshift of 13.2, or just 325 million years after the Big Bang. If the entire history of the universe were a 2-hour movie, then these galaxies are enabling us to watch for the very first time scenes from the first 2 to 5 minutes of the movie. This is important because we live in a universe of complexity, and the early universe was hydrogen, helium, and light, Hainline says. These are the galaxies that are starting the process of making the elements and the complexity that we see in the world all around us today. Before JWST, Hubble saw 2 luminous galaxies at such early times, redshifts greater than 10. Now, a whopping 93% of the galaxies JWST is picking up are new, never identified before. This, as Hainline declares, is the rest of the iceberg. The sample also provided opportunity for reassurance. Some in the community had been concerned that not all of these so-called early galaxies were really in the early universe. Astronomers first gauged their distances by a method that depended on measuring their brightness at each of several color bands. Using that method, it's possible for dusty, relatively nearby galaxies to masquerade as more distant sources. But the JADES team assuaged that concern. Of 42 galaxies followed up with spectra, from which astronomers can obtain more foolproof redshift measurements, there were no masqueraders. The hundreds of galaxies offer a view almost into the very opening scenes of the cosmos, and they show that things were different then. About a sixth of the early galaxies in the JADES sample are in the throes of star formation of a kind we don't see in the nearby universe, Ensley explains, marked by extremely bright emissions at certain wavelengths. Stars within very early galaxies are forming in these super-compact clumps, he adds, forming hundreds, perhaps thousands of these very massive young stars all at once, basically within the span of a couple million years. But they weren't on all the time. The low fraction of galaxies with such emission suggests that individual clumps would suddenly light up with new stars and then rest for some time. This bursty mode of star formation could explain the unexpectedly bright galaxies announced by other astronomers. They were simply looking at the galaxies fired up with unexpectedly intense star formation. However, while these findings explain 2 bright galaxies, they don't explain the 2 massive galaxies, another early, albeit controversial find from JWST data. The telescope has already painted a chaotic picture of the universe's earliest galaxies, as the most distant galaxies it captured emitted their light more than 13 billion years ago, according to preliminary calculations, just a few 100 million years after the moment that the entire universe was supposedly created 13.8 billion years ago, according to the Big Bang Theory. Observing more and more galaxies at times that barely succeed the supposed origin of the universe raises serious questions about the viability of the Big Bang Theory. how could bright, fully formed galaxies exist at what in cosmological terms would be regarded as a mere moment after the universe came into being? It's like watching an adult emerging fully formed from childbirth. According to the most widely accepted models of galaxy formation, giant galaxies are formed from small, faint clouds that gradually coalesce through cosmic mergers. This process takes billions of years. At a time when the universe was supposedly in its infancy, the theory predicts only the faintest dwarf galaxies, so small and faint that we would barely expect to see anything at all. Only later would giant galaxies form from cosmic mergers, and yet, here in the very first images sent back to us by JWST, we are already confronted with galactic behemoths, giants that simply could not have formed in the time allotted to them in the established theory of the Big Bang. In other words, the Big Bang theory is in trouble. And Webb's images could upend our understanding of the cosmos altogether, and we may have to rewrite all textbooks. As Alison Kirkpatrick, an astronomer at the University of Kansas, said, after seeing the first images from the James Webb Space Telescope, "I find myself lying awake at 3 a.m. wondering if everything I've ever done is wrong." And she isn't alone. Similar sentiments have been picked up by folk with an axe to grind about the Big Bang Theory. In particular, the independent scientist Eric Lerner, who has long advocated for an alternate model of cosmology, in August wrote an article entitled, "The Big Bang Didn't Happen." His piece, not surprisingly, went viral. Among other things, Lerner claims that the galaxies captured by the James Webb Space Telescope are too old and too numerous to be compatible with the Big Bang hypothesis, on the grounds that it is impossible for galaxies as large as the Milky Way to form in just a few 100 million years. The evidence, he says, points to a non-expanding universe, not an expanding one. And that would mean big trouble for the Big Bang Theory if it were true, but the truth is more interesting than the hype. The images captured by James Webb have given scientists a chance to rethink how the cosmos has evolved. One of the most common misconceptions of the Big Bang Theory pertains to its very definition. Rather than being a theory of the universe's origin, it's a theory of what happens after the moment of creation, if indeed there was one. For most of the past 2,500 years, the universe was believed to be timeless and unchanging. Stars twinkled forever. They were not born, they did not evolve, they did not die, they did not even change their positions in space relative to each other. The dawn of modern astronomy came and went. The beliefs around the movement of stars changed, and it was understood that local details might get altered. In any random corner of the cosmos, the universe as a whole was considered permanently unchanging. Even Albert Einstein assumed that the universe now must look like the universe a trillion years in the past and future. Then, in 1928, discoveries by an American astronomer caused this surety to waver. Data from Edwin Hubble's telescope appeared to show that galaxies were, in fact, all rushing apart, avoiding one another as if they had the plague. Jesuit astronomer Georges Lemaitre drew a different conclusion from Hubble's observations. He believed that Einstein's theory of general relativity could be used to show that the galaxies weren't moving apart through space. On the contrary, it was space itself that was expanding, and the galaxies were simply being carried along with it. Lemaitre noted that the universe may have existed in a pre-expansion state. He describes this state of the universe as a primeval atom, existing for immeasurable eons before it was somehow set in motion. Alternate theories were floated by astronomers keen to resurrect a timeless picture of the cosmos. This included a model by Fred Hoyle, a British astronomer, who ridiculed the idea that the universe's expansion began all at once, in what he deridingly coined a Big Bang. Then in 1964, a truly revolutionary discovery was made. Two astronomers, Robert Wilson and Arno Penzias, were using a radio telescope designed to examine satellite communications. They encountered a strange phenomenon. When they directed their telescope at any point in the sky, they found a weirdly persistent microwave signal. There was no point in the sky from which this signal did not emanate. They began to look closely at the idea that the universe had been very different in the past than it is now. This was implied by Lemaitre's idea and had been picked up in the early 1950s by two physicists, Ralph Alpher and George Gamow. Alpher and Gamow were building a model of cosmic history where the universe began in an incredibly hot, dense state. Gamow's models predicted that, approximately 300,000 years after the universe started expanding, space filled with a particular kind of electromagnetic radiation as matter particles cooled and changed their interactions. Not only that, this radiation would persist forever, a kind of fossil light. And it was this fossil light that Wilson and Penzias inadvertently picked up in their radio telescope. All the pieces of the jigsaw were perfectly slotting together. Wilson and Penzias had made an insurmountable breakthrough. The universe did indeed have a history. It had once expanded from a type of primeval atom, and it had continued to expand since. In doing so, it had left behind traceable electromagnetic emissions, which silently polluted the sky, invisibly goading desperate researchers waiting to be found by technology that was advanced enough. This important discovery, known in scientific circles as cosmic microwave background radiation, established cosmology as a science, and the Big Bang Theory as the foundation for all explorations of cosmic evolution. Since then, observations have further supported its veracity, and more details have bulked out the theory. And with these, the James Webb Space Telescope enters the story. To be a successful theory of cosmic evolution, the Big Bang must explain all aspects of how we got from back then to now. How did that transition occur? When and how did the cosmos start to form all the structures we see today? When did the first stars form? And when did the first galaxies form? Using ever more powerful supercomputers to simulate cosmic history, and even bigger telescopes to test the results of those simulations, researchers have developed a remarkably complete story. One of the most important aspects of that story is how stars and black holes began forming before galaxies did. The explanation for this is termed hierarchical structure formation, a sub-theory, if you like, of the Big Bang. Smaller structures, like stars, form first, it says, which then collect to form larger structures like galaxies. Many of this sub-theory's prediction were confirmed by the Hubble Space Telescope, which could look back to the era of galaxy formation. But Hubble's telescope had limitations, and astronomers needed to push back even further in time. Then, this year, along came the James Webb Space Telescope, built to see the first generation of stars emerging just a few 100 million years after the cosmic expansion began, and excited astronomers watched and waited for the telescope to confirm their predictions. And then it didn't. Instead of showing the formation of just a few small stars, which would satisfy the timeline of the hierarchical structure formation theory, the telescope revealed an anomaly. Whole galaxies had existed far before anyone had expected them to. And what did this mean for the history of the universe then? Well, a revolution is coming. Big Bang cosmology itself also suffered many adjustments in its history. And such revolutions can profoundly transform how we see and understand our world. But radical change is never easy to see coming. There's probably no way to tell whether the mysteries faced by cosmologists today are the signs of an imminent scientific revolution, or merely the last few loose ends of an incredibly successful scientific endeavor. Regardless, it's also great news. This is what should happen in science. New data should challenge our theories and force us to confront false assumptions we hadn't even known before we'd made them. The James Webb Space Telescope has done that for cosmologists. And as more data pours in, there are no doubt going to be a lot of happy, sleepless nights as scientists try to understand exactly what the telescope is telling them about the early cosmos. There is no question that we have made incredible progress in understanding our universe, its history, and its origin. But it is also undeniably that we are profoundly puzzled, especially when it comes to the earliest moments of cosmic history. I have no doubt that these moments hold incredible secrets, and perhaps the keys to a new scientific revolution. But our universe holds its secrets closely. It's up to us to coax those secrets from its grip, transforming them from mystery into discovery. Well, that's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit that bell so you never miss out on future episodes. And be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content like this and to always improve. As always, thanks for watching, and we'll see you next time.